So I know it's been a long day. You've been working very hard, and I also know that there's a wide background here. So I really aim to keep this talk very accessible. Occasionally I will go into a couple of details about how an algorithm works, but there'll always be a sort of high-level takeaway because not everybody will be familiar with some of the terminology, and I really do hope that I keep this at the level that is accessible to all of you. So the problem solved by public key cryptography, as you've been hearing today and maybe yesterday for the first time, some of you, is how to create secure communication across an insecure channel between two people who have never met or shared a secret. And so this was an example of a mathematical question that, when it was asked, did not really have an application, right? It was asked 20-something years before the application that made it essential to modern life came on board, namely the internet. Let me start with just a very quick overview of some milestones in the history of this. The subject was really born in 1977, so it's a mathematical subject that really rose out of this paper, New Directions in Cryptography by Diffie and Hellman. So it's available, and I encourage you to grab a copy of it and read it. It's very readable. So in this paper, which starts with the famous sentence, "We stand today on the brink of a revolution in cryptography." Wouldn't you love to write a paper that starts, "We stand today"? They defined a public key crypto system, but did not find an example of one, right? They defined secure key exchange and did find the example of this, the discrete log problem, which is now called the Diffie-Hellman problem. They defined digital signatures. And so I'm also sort of interested by the use of the word revolution here, because you see, this it was certainly a revolutionary idea, but it also emerged, as a sort of personal quest by Whit Diffie, that took place in a decade of great distrust of government. And you see, public key cryptography is a great equalizer between the private individual and the government. And so I think that word was really meant with several senses. So, as I said, they defined these concepts, and then shortly after, the first publicly disseminated, of course there was an earlier version of this, as we've come to know, out of British headquarters, the first publicly disseminated public key crypto system based on the factoring problem was announced by Rivest, Shamir, Edelman, called RSA. And about 7 years later, independently, Koblitz and Miller defined a public key crypto system based on translating the Diffie-Hellman problem into the context of elliptic curves. Okay, so the ingredients of public key cryptography, as set forth in this New Directions paper of Diffie and Hellman, we need a one-way function. So a one-way function is something that is easy to compute, but is hard to invert, hard to reverse. And of course, you really have to give some thought and attention to what you mean by hard to invert. And that is where the notion of of complexity and hardness of problems comes into play, which is so I'm going to be sort of skating over this right now, and in fact, this concept of one-way functions. Do we know that there are any one-way functions in any real sense? No, because we don't know what the relationship between P and NP and the complexity classes are. So we have a public key, and to encrypt, we use the public key. So we apply the function to this message. And everybody knows the algorithm, everybody knows the function, so now we have a message. And if it's a one-way function, if it's so hard to invert it, how do we get a hold, how does anybody decrypt? Well, when you decrypt to recover the input, In order to do that, you have to have a trapdoor, a private key. And so, for example, in the RSA system, which some of you said you have studied, you know that actually the fact is based on this problem of factoring a large number, which is a product of two primes. There really isn't, so far, a known trapdoor to that particular one-way function. And so what Ravesh, Shamir, and Edelman did was use that problem in a sort of sneakier way. Okay, so the outline of this particular lecture is to introduce integer lattices and the associated hard computational problems that are important in integer lattices, and to give several milestones in the development of lattice-based cryptography. In particular, I'm going to focus on NTRU, which is a lattice-based crypto system, and sketch some, if I have time, some recent developments, including touching on some aspects of fully homomorphic encryption, efficient signature schemes, and possibly hidden field isomorphisms, if there's time, which I'm sort of doubting. Okay, and along the way, you're going to learn all these acronyms. So this is an acronym-happy field, if happy is the right word. Okay, so let's start. So what is an integer lattice? So we're going to look at this. We can easily visualize this in 2 dimensions. So it's a regular array of points. And every point of the integer lattice, of this integer lattice that I've drawn in 2 dimensions, can be generated by those the vectors that form the basis of that parallelepiped. And when you have a basis for a lattice, that generates what's called a fundamental parallelepiped. So that's the region that I've drawn. And then the integer lattice is just those blocks of those repeating, infinitely. Okay, so that's the visual definition of this. In fact, what an integer lattice is in any dimension is, well, we start with a basis of vectors. So this is not the most general integer lattice, but these are the n-dimensional lattices in Rn that I'll be talking about. And then the lattice is just integer linear combinations of those basis vectors. So we just imagine we place some basis vectors down, and then we can walk around to all these points using integer linear combinations of these. And so a lattice can be represented as a matrix whose row vectors form the basis of the lattice. So now we connect lattices and matrices. And so once you represent the lattice as a matrix, you see that really a lattice has many different bases, right? You can start with one basis, and you make a change of basis by multiplying by another matrix which has determinant 1 and integer entries, right? Because this is an integer lattice. Okay, so there's lots of different bases you can choose for your lattice. And the 2 computational problems, the hard problems that are associated with integer lattices, are the shortest vector problem and the closest vector problem. Okay, so and they're related. So the shortest vector problem is this. So you're given a basis for a lattice. It could be, you're not told what kind of basis, but you're given some basis for the lattice, and now you're asked the question, what's the shortest vector in the lattice? Or the closest vector problem asks the following question. Given a random point in space, what's the closest point in the lattice to that random point in space? Okay, so let's take a look at this closest vector problem in 2 dimensions. So we have a random point in space, and we want to find the closest point in the integer lattice to this. So how would you solve this problem? Well, you take your basis, right, and you draw the fundamental parallelepiped around that point, right? And then you just pick the closest vertex in that fundamental parallelepiped. Okay, all's well, unless, of course, you don't happen to be using a good basis for this, right? If you're not using a basis where the the red vectors are a good basis for this lattice because they are as short as possible and as orthogonal as possible. And if you happen to be using the green vectors, which also form a basis for this lattice, and you draw the fundamental parallelepiped using those green vectors, and you pick a random point in space and you draw that fundamental parallelepiped around it, and you look at the vertices of that, you're not going to pick out the closest vector. So in other words, associated with this little visual exercise of finding the closest lattice point to a random point in space, I need to have on hand a particularly good collection, a good basis for my lattice, one where the basis vectors are as short as possible. Again, making a connection between this shortest vector problem and a lattice, right? If you knew what the shortest vector was, you could generate a new basis of your lattice. Okay, so a lattice has what we're going to call good and bad bases. And now, so the question is, so how hard are these problems? Well, in 2 dimensions, this problem is not hard at all. If you're given any basis for an integer lattice, there's an algorithm that goes back to Gauss to find the shortest possible basis for it. You can just sort of reduce it. You can do a kind of Graham-Schmidt process and reverse the order of the vectors. And then that algorithm breaks down as soon as you hit dimension 3. But there are algorithms that do find short basis vectors even when the dimension gets much higher than 2. And the most well-known was invented in 1982 by Lenstra, and Lavache. And this algorithm is guaranteed to work in polynomial time in the dimension of the lattice. So if you're in dimension 10, right, then some polynomial that depends on the number 10 in time, the running time, will generate, well, will it generate the shortest possible basis? Well, it's guaranteed to find a vector no larger than some large, in fact, multiple of your actual shortest vector. So that's what's guaranteed to happen in polynomial time. Now, in practice, in low dimensions, LLL works a lot better than this and finds really very short vectors. But finding very short vectors in high dimensions is currently exponentially hard. You try to run LLL in dimension, 150, and it's just not good. It's just not going to stop. It's not going to find something that's even remotely close. So once you have identified a hard problem, like the factoring problem for RSA, or the Diffie-Hellman problem, the discrete log problem, it's very tempting to try to build a crypto system, a public key crypto system that incorporates that hard problem. And the closest vector problem is actually an NP hard problem. So I think that you touched a little bit on the notion of complexity in the pre-talks yesterday. So that's, so it's one of these identifiable hard problems in the sense of complexity theory. Lattices, I think, first appeared in cryptanalysis, really, and one of the famous papers that used lattices is a paper of Ligarius and Odlyzko breaking what are called low-density subset sum problems. So let me just tell you a little bit about that, because that's relevant to something that has to do with the development of lattice cryptography and NTRU in particular. So the LLL algorithm was used to break a crypto system that was based on a problem called the subset sum, or the knapsack problem, in practical dimensions. So what is the knapsack problem? So the knapsack problem is you've got a basket full of integers, and you've got a sum of these integers, and the question is, which ones were used, right? So you can sort of phrase that as a dot product. You've got a sum, y, which is the dot product of a binary 0, 1 vector with another vector x. And in other words, that dot product picks out some of the integers and zeroes out the others. And if you're given the sum and you know the whole integer vector x, what's the vector a? So it's an inverse problem of some sort. Well, it's exponentially hard as the length of these vectors increases. And so there were proposed crypto systems that were built on some version of these knapsack problems where there was a special structure that was used. And basically, because it involves finding, see the inversion problem involves finding a short vector, right? A vector which just has zeros and ones in it. And it was that idea, that realization, that basically motivated Lagarius and Adlisco to show that you could actually use the LLL algorithm to represent this problem as the problem of finding a short vector in an integer lattice. And they wrote in this paper, it is probably prudent to assume that shortest non-zero vectors in lattices can be found efficiently. Okay. Lattice constructions. Now we're in the mid-90s. So there are some around 1996, several papers came out that took somewhat different directions, but basically brought lattices back into a constructive use in cryptography as opposed to cryptanalytic approach. A paper of ITI, which is famous on worst case lattice problems, ITI Dwork, ITI on small integer solution problems, Goldreich, Goldwasser, and HighLevel also based a crypto system on the closest vector problem. And a paper with Jeff Hofstein and Joe Silverman and I, where we designed an algorithm that basically was used the closest or shortest vector problem in the lattice, but in a particular class of lattices with a great deal of symmetry, because what we were after was something that was very efficient. Okay, so that's what I want to tell you a little bit more about. So N-True was presented at a rump session at Crypto in 1996. Do you know what a rump session is? Have you ever heard that term? So that was, yeah. So that's where it's like a contributed paper session, but not everything gets to be chosen, and the presenters are given 2 minutes, 4 minutes, 6 minutes to stand up and say, here's this idea. So that's what we did in 1996. Got 4 minutes, something like that. But we had a preprint, and so that was the first sort of presentation of the idea to the crypto community. Paper was subsequently submitted to and rejected by Crypto 97 and published a year later in Ants in 1998. Meanwhile, Cobbersmith and Shamir, that's the S in RSA, publish a paper in Eurocrypt 1997 called Lattice Attacks on N-True, in which they say, among other things, that with any improvements in lattice basis reduction, the temporary security of N-True would vanish. Okay, so here I'm going to pause because there's a long story here that I'm going to try to shorten considerably. The fact that Lagarius and Adlisco, very smart people, who really didn't believe that LLL would really fail to work, that lattice reductions methods would fail to work so profoundly in high dimensions, and the fact that there were these really powerful voices in the crypto community saying that they did not believe that lattice constructions could be appropriate for secure and efficient crypto systems really had quite a big impact on the development of the mathematics of lattice-based crypto at that time, and also on the company that we started to commercialize this crypto. So we totally underestimated the impact of this kind of powerful voice in a community to which we were outsiders, right? When you're an outsider in a community and you don't have a trusted network, then it's not easy to become part of what people feel is, probably, something worth considering. And so for many years, development of entry-related lattices and mathematics based on these lattices really was stalled, and it took really a new generation of cryptographers, and the subsequent work of Regev on learning with errors and ring-based mathematics, and Gentry's solution to fully homomorphic encryption using ideal lattices later to sort of really spark the development of this subject. So, entry was very efficient, and so we thought that very much more efficient than RSA or ECC still remains so. And so we really thought that there was an idea worth commercializing. I mean, the whole algorithm can be done on an 8-bit processor, tag and reader applications. We had a lot of ideas about that, but so we started this company, Entru Incorporated, and usually when I go into this story in any depth, I have a picture of a really wild roller coaster, but I'm just going to say I have that picture and skip over that part for now. Anyway, the company was actually acquired in 2009 by Security Innovation, and we very recently spun off a new company that holds the patents and deals with Internet of Things and vehicle-to-vehicle communications and applications to for post-quantum cryptography. So that company is called Onboard Security, and that satisfies my university's requirement to divulge my potential financial interests in that company. It's been like the longest get-rich-quick scheme on the face of the earth. Okay, so Entru Encrypt was accepted as an IEEE standard in 2008. Recognized by NIST as a potential practical family of cryptographic algorithms that were quantum resistant. And in 2011, accepted by the X998 standard for use in financial services. So, and then in 2000, so let me talk about a couple of the milestones in the mathematics of lattice crypto. As I mentioned, in 2004, Regev used Fourier analysis on lattices to produce an alternative PKC to ITI-DORC that also based on this worst case lattice problem, and introduced the well-known learning with errors, which you're going to learn about more in Kristen's lectures at the end of this week. Gentry in 2009 found a solution to a decades-old problem asked by Revest and I think I have a reference to the paper later, among others, and that the question of is there an encryption system where the ring operations commute with encryption? I'll say a little bit more about that later. But the idea was that Gentry used ideal lattices, which are a generalization of the lattices that form the foundation of Entru. So let me give you a few details, and I think that I'm going to try to tell you how this works, and as I said, for those of you that are not as familiar with these rings that I'm introducing and some of the operations, I want to say that we'll try to get a high-level takeaway from this, because I know it won't be so easy to understand if you're looking at it for the first time. So, so the Entru Encrypt works with polynomials that have integer coefficients. And these polynomials live in this ring of polynomials mod x to the n minus 1, which means that whenever you see x to the n, you just replace it by 1. In other words, the multiplication rule is this convolution multiplication. And so to multiply two polynomials together that are using this rule and keeping it in this ring, the kth coefficient turns out to have this form. Notice that all the indices just add up to k. Now, the coefficients can also be reduced modulo various integers p and q, and in fact there's going to be a double reduction that is important to the encryption and decryption problem. And so when Joe Silverman and I got involved in this project, Jeff Hofstein had been thinking about this for some time, and in particular he had this idea of disguising a distribution using this double reduction, first modulo one prime and then modulo another. And now you'll see this happening in various papers in cryptography, like it's part of the folklore. Well, it actually, I think, appeared here first. The inverse, so now if you have a polynomial in this ring with integer coefficients mod q, then you can attempt to find an inverse of it. And actually fairly many of these polynomials do have inverses. So I give an example, but I'm going to skip it. Okay, so now I want to define the keys. So in a public key system, you have a public key that everybody sees. You have a private key that you keep secret. You have an algorithm that everybody knows. Okay, so there's lots of parameters here, and that's one of the tough things about NTRU is that when you're looking at trying to analyze the security of it, you have a lot of different parameters that are related to one another, and that all affect the security level of the algorithm. Okay, so n is going to be some large number. N will be 500, let's say, in the several hundreds. And p and q are going to be relatively prime. P is going to be small. Maybe for now, think of p as 3. P is so when you're reducing mod p, then you just have zeros, ones, and minus ones lying around. Okay, so we're going to generate a private key by choosing some random polynomials with small coefficients. Small means zeros, ones, or minus ones. And there's also going to be a certain number of ones and a certain number of minus ones and zeros, so that we can really sort of pin down the size of these polynomials and understand, as measured by, we can think of the polynomial as a vector, right? A polynomial is the vector of its coefficients, and so we can talk about its size by measuring it in Euclidean, in the Euclidean sense. Okay, so if we generate an f and a g and they don't have all the inverses that we want, we're going to throw them away and start over. Until we get an f and a g where the f has an inverse modulo this q. How big is q? Q is on the order of the size of n, let's say. So we have an inverse mod q and we have an inverse mod 3. And now the public key is going to be that quantity. G is small, fq is the inverse of f. So when we take the inverse of a small polynomial, what does it look like? It looks pretty random, actually. It doesn't look like it came from a small polynomial. It just looks like some random mod q thing. And when we multiply by g, we're picking out some of the coefficients and then not others, right? Because g just has zeros, ones, and minus ones in it. And we also get something that looks very random. And in fact, you can make that precise, as Damian Stela did later in a paper in which he sampled from Gaussians. But anyway, it just looks random. And so that's your public key. It just looks like a random mod q vector or polynomial. And that's what you give to everybody, and f is secret. Okay, so the plain text, so what you're going to encrypt, the message, is another small vector. Just zeros, ones, and minus ones. That's your message. And the way that you do that is the following. That's the encryption of M. So you take M and you add, so that's what somebody does to send you a message. They're looking at your public key H and they say, okay, take M and then add to that the following thing. Take the public key mix it up a little bit more by multiplying it by a random small r. Just sort of another mixing it up again. And then multiply that by the number 3, the p, and add it to m. Fine. So that's the encryption. How does somebody compute, how does somebody find m who knows the secret key f? Well, the way you do that is you start with your encryption and you multiply it by f. And what does that do? Remember that h is f inverse times g. So if I multiply h by f, I just get back g again. So there's g. And then what I have in that last line, you see, is everything is done mod q, right? All these reductions and inverses and so forth. So at the end, I get this quantity p times r times g plus m times f. And everything is small. M is small, f is small, so is g, so is r, p is 3. And I have this thing mod q, which is 500. Now, if I choose my parameters carefully, that will not be just a mod q representation of that quantity. That will be the real thing. That will be the real quantity over the integers. And since it's the real thing, I can then mod out by p and really get m times f. And then I can multiply by my f inverse mod p and really get m. So the high level version of this is that here's the n-true hard problem, really. You can represent it as a lattice problem, but it's actually a kind of factoring problem. Given h equals f inverse times g, find g and f. And the reason that you can formulate this as a shortest vector in a problem is that when you multiply these polynomials together, you're using convolution multiplication, right? That's what it means to multiply in this ring x to the n minus 1. And convolution multiplication of a vector is the multiplication of that vector by a circulant matrix, right? If I take a vector, if I take the vector f, f0, f1, f2, etc., and I multiply it by that matrix, that circulant matrix, that's my public key, I get exactly convolution multiplication. So the convolution multiplication of two vectors is the same as a matrix acting on a vector, where the matrix is that circulant matrix. And so in other words, that's the lattice that's associated with n-true, or rather a balancing of that. And why do I have the q's down there? Because once I multiply f times h, I have to mod out by q. So, in other words, heuristically, we think of an n-true lattice as the identity h0q. The vectors are the vectors. The elements are are polynomials in this ring, so what we're giving to the public is this bad basis because h is large. But you notice that this is a 2n by 2n lattice where everything is q is large, h is large, and there's a secret basis which contains the vectors f and g, which is short. And in fact, the vector fg is an element of this lattice. So the secret key is in fact a short basis vector times in this lattice. Because if I were to multiply this matrix by f and the thing that you have to mod out to get g, I pick up fg. So that's what I mean by the matrix having a lot of structure. So there's a shortest vector problem, but it's in a class of lattices with a lot of structure. Okay, so quantifying the security really takes a lot. Took a lot of years of computer experiments to try to figure out what the parameters are that we needed to modify. And see, that was the other thing when we went to present this at Crypto. We had done some of this analysis, but we didn't have a complete analysis of parameter choices and security, and that was also so that was part of the issue in this cultural divide between what we were doing and the crypto community was doing. We weren't communicating what we were doing in the same way that they were used to receiving it. So we did not have a sort of complete, here's the right parameter choices and security choices. We just went there like mathematicians saying, hey, look at this neat idea. And they would, didn't think it was that neat at first. Okay, but why dwell on this? All right. So with parameter choices and n-true, there's a lot of work that has to be done to figure out how to choose the relationships between n, which has to be prime, the small p, which doesn't have to be a number, it could even be another small polynomial, q, the number of non-zero coefficients of f and g, because you want to make sure that everything is chosen so that after you multiply by f, you've squashed things down so much that mod q is the same as over the integers. Okay, so quantifying the difficulty of certain lattice problems. Okay, so there's been a lot of work in the last 10 years on quantifying these difficulties, and in particular I wanted to point out that there's now, so our parameter choices in security were always based on looking at this Gaussian shortest expected shortest vector in the lattices, but there's a class of lattices where this has actually been shown to be sort of closely related to the ratio of the target vector and the actual and the Gaussian expected shortest. Okay, so some comparisons. So all right, so now I wanted to talk a little bit about quantum algorithms and lattice problems, which is the focus of Kristen's lectures and some things that you've been hearing about in some of the seminars. So quantum computing, as you've been hearing, efficiently solves certain problems. Actually, they actually what they're solving are certain what are called hidden subgroup problems. And so that means you have a group G, and you have a set X, and H is a subgroup of G, and F is a mapping from G into X, and this hides H if F is constant on cosets of H. Okay, so if you haven't, if this is not so familiar, I'm just saying there's a problem in groups called the hidden subgroup problem, so the hidden subgroup problem is given evaluations of F, find H. And what Shor's algorithm does is, yes.
So what does it mean that for it to hide that none of the elements map into?
It's constant. It's constant on cosets. So F maps G into X and is said to hide H if it is constant on cosets of H.
All right.
And so the hidden subgroup problem is given the evaluations of F, determine H. And what Shor's algorithm does is solve the hidden subgroup problem for finite abelian groups. Regev showed that the shortest vector problem in an integer lattice there would be a quantum algorithm for that if you could solve this hidden subgroup problem for dihedral groups. So that sort of puts this into a context where there's some interesting work in group theory to be done. So where are we now in quantum computing? Well, you've been hearing a little bit, you briefly heard about how Microsoft has been taking an approach from the point of view of topological quantum computing, which nobody seems to know what that is. Certainly I don't. And now there are some quantum simulators, but really only a true quantum computer can run Shor's algorithm and currently break PKCs. I just love that picture. That's IBM's 51-qubit quantum computer being cooled to near 0 degrees in order to solve a few problems. Okay, so I wanted to spend just the last 10 minutes saying something about digital signatures because it introduces another circle of ideas, which was very beautiful, introduced a few years ago by well, I think I have to see the name to pronounce it, but we'll get there. So, all right, so what is a digital signature? So from New Directions in Cryptography, Diffie-Hellman, we have, in order to have a purely digital replacement for a paper instrument, each user must be able to produce a message whose authenticity can be checked by anyone, but which could not have been produced by anyone else, right? So if I'm signing something digitally, I've got my public and private key. You see my public key. When I sign something, I'm producing something which is bound to that document I am signing. It's connected, to it by some formula, but only the holder of the private key could produce that. That's what a digital signature must do. And so, of course, when you sign a document, so it's even a harder problem than the encryption problem in many senses, because when you're signing a document, you're revealing that you have the private key, but you don't want to reveal anything about the private key, right? So let's look at an example of using this closest vector problem or shortest vector problem in an integer lattice to produce a digital signature. Okay, so my document is going to be a random point in space. Okay, so that's my target, okay? Now, my signature is going to be the closest lattice point, right? Because if you got the bad basis and I've got the good basis, only the person with the good basis is going to be able to produce the closest lattice point to that target point, right? So I've signed that document. Okay, sounds good, except, right, and so this is, so you have to be using the, that slide should have come earlier. You have to be using the good basis because you're going to pick one of the vertices of that parallelepiped and say that's the closest point to my target. But now, as you sign your document, let me go back to this picture. As you sign your document, right, that's your target, and then you produce the closest point in the lattice, and the difference between those 2 points lies in the fundamental parallelepiped, right? And then you sign another document, right? So you have another target point, and then you sign it. Now you produce another point in the fundamental parallelepiped, and eventually, after you sign enough documents, you start filling out the shape of the fundamental parallelepiped. So in other words, you're revealing something about your secret. So inherently, in using this problem with integer lattices, you have to combat the issue of revealing something about the private key as soon as sufficiently many signatures are generated. So one of these signature schemes that we put out using Entru, we estimated that we could get away with signing 1 million or more documents. We knew that there was signature leakage, but we combated that with some operations, and then Nguyen and Regev showed that really no, about 1,000 would do it. So that didn't work, and so in the subsequent couple of years, some really interesting new tools emerged that allow us to make this a little less efficient, but still an incredibly interesting signature scheme. So what I want to talk about is this concept of rejection sampling. So this is an idea, so now we're bringing some statistics into cryptography, when there's probably a lot more mathematics, including statistics, that should be brought into cryptography. So this was first used in lattice constructions by Lubashevsky. So let me skip to the point. Okay, where's the point? There we go. Okay, so I'm going to tell you what rejection sampling is from a statistics point of view, and then I'm going to say what its use was in digital signatures. Okay, so the setup is this. You have two probability distributions with the property that one of the distributions times some large number, lies above another. So that's your setup. Not every probability distribution, right, satisfies this, but you've got a pair of probability distributions where as soon as you dilate the one enough, it will lie above the other. now we're going to generate, this is an algorithm, by the way, that goes back to von Neumann. Now we're going to generate a uniform probability distribution on 0, 1, right? That's what U is. Now we're going to take a sample of X from the probability distribution G. And now we're going to decide whether to keep it or reject it. And we're going to accept it only if f of x divided by m times g of x, which is less than 1, right, by our relation there, lies above u of x. The algorithm can be shown to generate samples from f. Okay, so in other words, this is a way, suppose that you really want to generate samples from f, but it's really hard to, okay? But now you have this other probability distribution that lies above this by a certain, when you multiply it by m, and it's easy to find sample from that. So in other words, in statistics, this is used to generate samples of a distribution that's hard to sample from, by sampling from an easier one. Let me give you the most basic example of this in action. And suppose that you want to sample, suppose you want to find a uniform sample of points from that circle. Okay? Now, the uniform distribution on the square and the uniform distribution on the circle satisfy that relationship with a certain constant. Right? The uniform distribution on the square, lies below the uniform distribution on the circle, but if you multiply it by something, it will be above. Okay, so it's easy to sample something uniformly in the square, right? And so now what we do, the rejection sampling argument is extremely simple. In this case, we're simply going to reject a point when we sample from the square if it doesn't lie in the circle. And that will generate a uniform sample from the circle. But you see, the interesting thing for cryptography, and that was Lubashevsky's idea, which is so cool, is that actually you can use this to hide a distribution. Right? Because if you really, if the distribution, if the square distribution is your fundamental parallelepiped, and you don't want to reveal it, right? You should be, you're going to generate samples from it, but you should reject a certain number of them so that they look like they have other distribution. So I see that yes.
So then you went after the signature. If in the case that you reject, you don't sign it, or?
Right, so you don't, in other words, when you're producing a signature, you go through an algorithm that generates a certain sample, like the one that I said by finding the closest point in the lattice, okay? But if you want those samples to look like they're something, they come from a different distribution, you should be rejecting a certain collection of them. In other words, you're not going to produce every possible, sample in this. I mean, it's a little more complicated than this, but that's the general scheme is that you can hide some of the distribution that your natural sample is revealing by rejecting a certain number of them. Yes?
Are you going to leak any information by the ones that you reject?
Well, you don't reveal the ones you reject. In other words, when you produce a signature in a document, you're going to make multiple tries before you do this.
Nobody would know anything.
So no, right. I mean, so it's not quite as simplistic as rejecting the samples. Not producing. In other words, you don't really produce the closest point in the lattice. You produce something within some cloud that is still very hard to produce unless you know the shortest vector problem. Yeah. Okay, so given the time, I think I'm just going to state what fully homomorphic encryption is. And there's a lot of work and an expert in the audience who is going to be giving several more lectures, and Kristen will probably mention this more. So in 2009, and the reason I mention this is that this was solved initially by ideal lattices, which It goes back to those lattices that were introduced in the mid-90s. So Craig Gentry in 2009 solved the following open problem, which was posed in this paper in 1978. You know, can computations on encrypted data equal the encrypted results of the computations? In other words, can you find an encryption algorithm that commutes with the ring operations of plus and times? And so what he did this by a technique of bootstrapping, which is turning a scheme that is really partly homomorphic into a fully homomorphic scheme. And a partly homomorphic scheme is the one like NTRU, where, you know, if you encrypt it, if you take the encryption of the sum of two messages, which is still pretty small, you'll get the encryption of you'll get the sum of the encryptions. But you can't do this forever, because as soon as you add up a huge number of these M's, then you're not in this small range anymore, and the whole encryption algorithm breaks down. So what Gentry did was produce a sort of theoretical solution to this problem. It wasn't ready to be implemented practically. But before his work, nobody even knew that such a thing was possible. And what he did in this was something that sort of reminds me of the things that some of the ideas that really that go into Gödel's theorem and self-reference. What he did was produce an encryption algorithm that was partly homomorphic in the sense that it could decrypt its own decryption circuit was within the scope of the things that it could be, that would be partly homomorphic. And so at some point you're encrypting messages, and then you get to the point where you can't go any farther in your sums, and then you sort of re-encrypt everything. And in order to do that re-encryption process, you have to be able to do that within the scope of the encryption scheme. It was kind of a wild paper that he wrote. So fully homomorphic encryption is an algorithm that. Okay, so I'm still describing what Gentry did. Well, okay, so I'll skip that. Okay, so let me just give you some very selected references in this subject, because there's a ton more, but I would say that the last two papers, Fully Homomorphic Encryption for Mathematicians by Alice Silverberg, is a very nice introduction for people with a mathematical background. And then for a reference to some lattice cryptography, there's a 2016 manuscript of Peichert's Decade of Lattice Cryptography, which talks about some of the modern developments since, say, about 2008. And I think that's it. Thanks.